Okay, so we've only got one wimpy equation to use, but we can come up with some other ones too. Some of them we can come up with even just by kind of thinking about the relationships between the kinematic quantities. Now, real quick, what are the kinematic quantities? So we know obviously time is one of them, right? Time is like that's our universal variable. Time is just how what time does for us is it allows us to separate events, right? And so we'll talk a lot about, a good way to think about kinematics is like if you're filming a video and you look at certain frames in the video, right? The time is what separates the frames in the video, okay? What about the other ones? What else have we got? Say it again.
Distance.
Distance, but instead of distance, position, right? So we've got position. Let's do it this way. We've got position. The variable the book uses is a d, right? And that's typically a function of time, right? What else have we got?
Acceleration.
Okay, and then what comes before that, maybe? Velocity. So velocity v of t, right? Now and technically these are vectors, aren't they? So probably, I get lazy and always write, probably we should write that. What's the definition of velocity? At least average velocity. So v bar, average velocity is what? Good, so say it again. Change of position. So that's delta d. What's another name for that? Just hang on, no. Displacement. Yeah, displacement, right? All this is change in position. That's just position, final position minus initial position, right? So displacement over time, right? Make sense? Okay. Along with that, I want you to notice something here. What about acceleration? What's average acceleration? It's equal to change in velocity over change in time. Now, how about that? That fits with what we said yesterday, in fact. We looked at a bunch of examples yesterday of kinematics graphs. We looked at position time graphs, we looked at velocity time graphs, and we looked at acceleration time graphs, right? What did we say about the relationship between, you fill in the blank, between velocity and position and acceleration and velocity? So fill in the blank. Velocity is to position as acceleration is to velocity, right? Make sense? Now think what we said about that. If we just take a very brief look at our kinematics graphs, right? If I take an example where I've got a position time graph, and it does something like that, let's say, what could you tell me about velocity? How does it relate to that? Okay, it's constant positive because the slope of the position function equals the value of the velocity function, right? Does that make sense? So if I were to graph the velocity, let's just graph it on the same graph. So let's say that's d, then wouldn't v just look like that? Okay. What if I had a velocity time graph, and so here's my velocity. What can you tell me about the acceleration? Same deal, right? Because the slope of a velocity function is equal to the What? The value of acceleration, right. So once again, velocity is to displacement as acceleration is to velocity. Make sense? Okay, so we got that relationship. So we can exploit that. So we have already one kind of wimpy kinematics equation. We knew this from section 5.1. Position equals, you finish it, initial position plus VT, right? Make sense? Okay. So, and this is considered to be, well, let's leave it like that for now. Okay, so what could we do to that if we take advantage of that relationship that we just discussed? Velocity is to position as acceleration is to velocity. So could you come up with maybe a corresponding equation for velocity? What do you think?
B equals V initial plus acceleration times.
Yeah, it makes sense, doesn't it? Right? V is to D as A is to B, right? Now we can get those from another place too. Really, if I solve this equation up here, what is delta D? That's just D minus D naught, isn't it? Right? So if I rewrite this, this is really just V bar equals D minus D naught. Now what's delta T? Explain to me, what is delta T? So it's what? What's delta anything?
Change.
So it's changing, right? So it's going to be the final time minus the initial time. But what's the initial time? 0. That's when we start our stopwatch, isn't it? I mean, almost always we're going to set the initial time to 0. So couldn't we just really say that delta T, if we're starting at 0, is T? Right? Okay. So what happens here if I multiply by T and add D naught? We just get that? See that? Okay. And keep in mind that as far as we're concerned in this physics class, that's an average velocity, right? But it would work in calculus. We'll see that it works for non-constant velocities too, or non-average velocities too. Okay. And I'll show you an example of that in a second. So same thing here, right? If I write the definition of change in velocity as V minus V naught over T, same deal. If I multiply by T and add V naught, don't I just get that? So these two equations are nothing more than restatements of the definition of velocity, average velocity, and the definition of average acceleration, right? That's it. Okay, make sense? So if we wanted to, we could write this average velocity as a true average too, right? What's the average? How do I calculate the average of any quantity? How do I calculate the average of numbers? What's the average of 4 and 16? 4 and 16. 10. How'd you get it? Add them and divide by 2, right? So I could also say, if I wanted to, I could really say that V bar is just equal to V plus V naught over 2 if I want to, right? And calculate the average that way. Does that make sense? Okay. What else do I get here? So I get another equation I'm just going to give to you. Actually, before we do that, let's use one of these a little bit. So how about this? Let's say here's the situation. We've got a guy standing on the edge of a cliff. Okay, let's say that the cliff is 20 meters high, and he's going to throw a ball straight up, and he's going to throw the ball up with, he's going to lead his hand going 15 meters per second, let's say, okay? So he throws it that way at 15 meters per second. And I want to know how fast is the ball going after 1 second, okay? And we're missing something from this picture here, though. There's something else we need to take into account. Say it again. Gravity. Yeah, what's gravity? I mean, what kind of, is it a velocity? Is it, what is it? It's actually, your weight is a force, but gravity is an acceleration, right? What gravity, and this is something, the book doesn't really talk about this, I think, until next chapter, but there's no reason. Oh, we know it does, never mind. What number does it give for gravity? 2. So it does use negative 9.8. Okay. If I drop this pin, what's happening, right? I mean, it's accelerating towards the middle of the earth, really towards the floor, sure, but it really wants to go to the middle of the earth. The floor just stops it, right? What is the value of that? Well, we talked about this yesterday. It's roughly 9.8, right? We could, if we're doing really quick calculations, and maybe not on a test, but if we're doing really quick calculations, like if you want to just really quickly crank out an idea of where this thing's going to be, what's a little more convenient value to use than 9.8? Yeah, we could just use 10, couldn't we? Right. So this thing is approximately, exactly 9.80, but approximately 10 meters per second of acceleration. So when I drop it, it's picking up speed in that direction, the negative direction. That's why we give it a negative sign. Good luck. After 1 second, how fast is it going to be going? You know? Now think what this means. If the acceleration of gravity is negative 10 meters per second squared, what that really is, or negative 9.8, and we assign lowercase g is what we use to represent the acceleration of gravity. So it's roughly equal to negative 9.80 meters per second. That's what a meter per second squared is. So let me ask you again. After 1 second, how fast is this pin falling? 9.8, right? Because it's picking up 9.8 meters per second of downward velocity every second. After 2 seconds, how fast would it be going? Roughly 20, exactly 19.6-ish, right? Down. So the speed would be 19.6, the velocity would be negative 19.6, right? Make sense? Okay, so we need something else here. We also know that because this is on Earth, we know that the acceleration is equal to g, which is, we'll call it, is roughly equal to negative 10 meters per second squared. Okay? But I asked you one other thing about this. I said I wanted to know how fast the ball was going, what? There's another part to my question, remember?
After 1.
After 1 second. So I know something else, don't I? What else do I know? Time. I know that the time of the event I'm interested in, I'm telling you that the time is 1 second. So we're going to run the movie forward 1 second, and at that moment I want to know how fast it's going, right? So let's put all that stuff, let's write all that stuff, compile. All the stuff that we're given. This is the stuff we're given. We know that t equals 1 second. I know that acceleration is roughly negative 10 meters per second squared. I know that, what's this, tell me? Yeah, what would you call that? Okay, but what, I mean, it's when,
That's where it starts.
okay, so what do we call that? Velocity, initial velocity, right. So when we start, the velocity is 15 meters per second. Positive or negative? Positive, because it's up. And we know also that the displacement, I guess, or the height, position, is 20 meters. What are we trying to find? Okay. So, we'll say it again. Final velocity, which is just kind of velocity, right? We want to know the velocity at 1 second. So we're looking for velocity, right? Okay, why do I write that stuff down? Because that helps us choose the appropriate kinematics equation. What are the criteria we follow when we're trying to choose the kinematics equation, you suppose? We don't really have many choices now, but we're going to get more as time passes. What do you think? I would want to pick an equation that what? I know all this stuff. I'm trying to find that. So the equation should probably incorporate what?
All that stuff. Yeah.
All that stuff that I know, but also just one unknown, right? So I want to pick an equation that only involves the thing I'm looking for and things that I already know, right? Well, that's our new equation, isn't it? So if we pick the equation v of t, right, equals, what was it again? Initial velocity plus, yeah, that's stuff I know, isn't it? So if I plug in what I know, that's positive 15 meters per second plus negative 10 meters per second squared times 1 second, right? Okay, so what happens here? When I numerically, when I multiply the numbers together, I get what? So all this stuff, good, it's gonna give me a, perfect, it's gonna give me a negative 10, and remember we treat units like variables. So if I have a second on top and second squared on the bottom, I'll just cancel 1 second from each, right? And so I get negative 10, oops, meters per second added to 15 meters per second. So what's my answer? 5 meters per second, and that's, whoops, that's my V of 1, right? Make sense? Okay. So you kind of see the purpose of these kinematics equations. They help us find the kinematic quantities at the time of the event we're interested in, right? Okay, let me give you another one. Let's take this same situation and let's change it slightly. Let's say, here's what we're going to say. So, can I erase all this stuff? So I want the picture to be almost the same. Okay, only this time I'm going to say, instead of this, I'm going to say that after 2 seconds, the ball is traveling up at 2 meters per second. Okay. I'm asking, how fast did he throw the ball? Okay, so what is the quantity I'm looking for there? Initial velocity. Okay, what am I given in this case? A lot of the same stuff, right? So, by the way, did that position ever even come into play?
No.
Never did it? It was irrelevant. It was extra information that we didn't need. I mean, I can write it down if I want to. Probably not going to need it this time either. We knew acceleration is roughly negative 10. What else do we know? Time, okay, good. T is what? 2 seconds, good. And what else? Final velocity, so just do velocity, right? Velocity equals positive or negative? Positive, it's going up at 2 meters per second, and we're looking for initial velocity, right? So we start with the same equation, don't we? Okay? So we start with the equation V equals V naught plus AT, right? Okay, now we have some choices here. And really, I don't care how you approach this. I have a suggestion, but you may not want to follow this. I could plug all the stuff in right now and then solve for the unknown, right? What's going to be left at the end? That going to be the unknown? Okay, or what else could I do? Okay, I could algebraically isolate the unknown, and then plug and chug? What do you think is probably easiest? I'd say the second, because variables, symbols are easier to manage than numbers can get really cumbersome, right? The symbols are nice and compact. So I would say, in my opinion, it's better to isolate the unknown and then plug and chug. So what do I have to do to get that V naught by itself? Just subtract AT, right? So would you agree I'm gonna end up with V naught on one side by itself? On the other side, I've already got a V and I'm gonna subtract an AT, right? And so if I plug all that stuff in, what do we get? So V is 2 minus negative 10 times 2, and I'll just leave the units off this time. I used all standard units, so everything should work out. So what does that give me numerically? Yeah, 22. 2 plus 20. What are the units going to be of my initial velocity? Yeah, meters per second. Good. So there it is. 22 meters per second must be the speed at which the ball was thrown upward, right? Yes?
Is the acceleration always going to be -10?
Yeah, well, technically it's negative 9.80, but I'm just to make the calculations easier, we're just using negative 10. Okay, make sense? Okay, let's answer a really, really good one. Okay, let's say this. Let's say that we are, okay, this time we're going to be standing on the edge of a high cliff. This time it's going to be 300 meters tall. Okay. And this time the person that we're interested in, he's or she is going to shoot a rifle straight up in the air. So we're going to track the trajectory of this rifle ball. Okay, it's going to go straight up in the air, and then it's just going to come back down. Okay, the question that we want to ask here is, when does it hit the ground? When meaning time. Yeah, how much time does it take to hit the ground? Now, this bullet happens to be coated with sliprium, which will negate all the effects of air resistance. You buy it at the Acme store. It's very expensive to get, but it's so we're going to be able to ignore wind resistance. Now, in reality, that's not at all the way it would be. It would be wind resistance would have a tremendous impact on what the bullet actually does. But we'll just ignore that, okay, for now. So I'm going to tell you that the bullet leaves the gun with a velocity of 1,000 meters per second. So maybe we could represent that like this. So there's the velocity. Okay. And what else do we know? And let's be more exact this time. What else do we know about this situation? Acceleration of gravity is, and let's say negative 9.80 this time. Let's be a little more exact. So the acceleration is negative 9.80 meters per second squared. Okay, that's going to require a different equation, right? Because this time we don't have enough information to find a time from when this thing gets to the ground level. Okay, so we need something else. We're going to add another equation to our list. Here's the equation. Yeah, here's the equation we get to add. Now, I'm just going to give this one to you. We could prove this one algebraically, but it takes a long time to do and it's pretty hokey. But in calculus, we will prove this one from basic principles very, very simply in a while. Not now. This is going to be like in a month and a half or something, let's say. Okay, so here's the other one we get. Position equals initial position plus initial velocity times time plus 1/2 AT squared. Okay. All right, so now I'm going to just transcribe that onto the other page. And let's do this problem. This is a cool problem. You're going to like this one. So here's our equation. Okay, so we know everything up there except what? Time. We actually actually know displacement too. What is the position gonna be at the event we're interested in? So we're starting at a height of 300 meters, and we wanna know this bullet's gonna go way up in the air and it's gonna come down. We wanna know when it hits the ground. So what's the position gonna be when it hits the ground? Zero. Okay, that makes sense? Okay, yeah, so we know everything we need then, don't we? We know that initial position is 300. We know that initial velocity is 1,000. And we know acceleration is negative 9.8. Good. And we also know that final position is 0. Okay, that's good. Everything is accounted for up here except t. What do you notice about t in that equation? Oh, yeah, it shows up twice. Okay. How about that? So what do we get when we plug all this stuff in there? So we're gonna get 0 equals 300, right, we'll just leave the units off, right? Plus 1,000t. 1,000t plus 1/2 times negative 9.80 t squared. Okay. Let's go ahead and put this into kind of a standard form. What am I going to get here if I multiply 1/2 times negative 9.8? It's going to give me a negative answer, isn't it? Negative 4.9. When we're dealing with quadratic equations, we really don't want a, the coefficient of x squared, or t squared in this case, to be negative. Remember talking about that? We always want to make it positive when we get it into standard form. So instead of writing it this way as negative 4.9 t squared plus 1,000t plus 300 equals 0, right? Standard form just means set equal to 0, right? What do we do to change the signs? Well, we could move everything to the other side, or we could multiply or divide by negative 1. That just gives us 4.9 t squared minus 1,000t minus 300 equals 0. So we've got a quadratic equation there. In physics, we don't really need to worry about solving that using the quadratic formula. We could, but let's just use technology, right? We just want to, the physics part was we had to set up some kind of a mathematical equation, some kind of a function that we could evaluate, maybe cheating and using a calculator or technology, right? So let's do that. Let's cheat a little bit. So if I take a calculator here, I'm going to show you something kind of cool. Okay, how do you solve quadratic equations? Program, and what do you usually use? Aqueduct? I got a better one for you. I think a better one. I think a better one. You can decide. So here's my better one. So I want to do, I'm going to have you go to apps, polysmolk 2. What's great about this one is it doesn't just solve quadratics. Polysmolk 2. You don't have it on there?
No, I have a lot on my.
So what you can do then, just hit alpha P and it'll skip you down to the P's. And you can go apps. So let me do that again. So the one that we want is, you go apps, and it's that one. What that stands for is polynomial simultaneous equation solver, and this is the second version of it. So that's fine if you don't. I don't know. I think you can put it on those, but I'm not sure. I think you can. I think it comes stock on all the new TIs, but we can add it too. It's not a big deal. So, and you can always use Aqueduct. It's fine. So we're going to go to polynomial root finder. What's nice about this is it doesn't just solve quadratics. I can pick the order of the polynomial that I want to solve. Pretty cool, right? It's going to give me all the real roots. It'll actually give me real roots or even imaginary roots. Okay. So a quadratic is really just a second degree polynomial or second order polynomial. So we'll just leave that at 2 as kind of our default setting. And let's go down, and I want this to be decimals, how about? So I'm gonna change that to decimals, but it'll even try to give me fractions, which is pretty cool, right, for my answers. Everything else looks good. So we just go down and hit next, using this soft button down here. And now we have to just put in whatever the coefficients are. So our coefficients are, if we look at this equation, we get 4.9, right, is the coefficient of, well, they're calling it x squared. For us, those x's are really t's, right? Okay. So 4.9, go down. Then we have negative 1,000, okay? And negative 300. Okay, and then we just go up and hit solve. Look what it does. Okay. So it gives us 2 answers. Let's just say we had all these to 3 sig figs. How about? Let's say we had everything, pretend we had everything to 3 sig figs. So what are my times gonna be? I get t equals, whoops. What do I get for my times? I either get 204 seconds, or t equals negative 0.30. Okay. We're used to dealing with multiple solutions. How do we handle that? Yeah, so which one do we probably want? The positive one? Negative one, just a bunch of nonsense probably, right? So the positive one, it takes about 204 seconds for that bullet to go up and come back down and hit the ground below. Okay, good. That negative one is not really nonsense though. There's something there. It means something. Anybody hazard a guess as to what that means? Now think about the question that we asked the physics gods. We didn't really ask the physics gods a question about a rifle. What we asked the physics gods was this question, right? All we specified for the physics gods was that when the position is 300, when we're going to call that our initial position, that's when we're starting our stopwatch, the velocity is positive 1,000 and the acceleration is negative 9.8. We want to know how much time is it going to take to get from that event to the event where position is 0. Okay? As far as the physics gods are concerned, that could be a rifle, or it might just be a pipe. And maybe, right, because we didn't tell them anything specific, right? It might just be that somebody, instead of shooting a rifle, is holding a pipe out there, and somebody actually fired a bullet from ground level 0.3 of a second earlier, right? What did that bullet do? It just went straight up through the pipe and out the top. Okay, how fast was it going when it left the pipe? That fast, right? Isn't that cool? Right? You see that? We didn't really specify to the physics gods. We have to interpret their response in terms of our specific situation. So if this really was a rifle, which we assume it was, then this answer really doesn't make sense, right? This is the answer that makes sense. But this one really does have some physical meaning, right? It just means that if somebody had actually fired that bullet from ground level a little bit earlier, and it would have had to have been, everybody agree, it would have had to have been a little faster than 1,000, because it's lost a little bit of velocity on the way up. But we could even calculate that if we wanted to, right? That's another situation that also fits these parameters. So what does it mean? Does it make sense then when we say something like a negative 0.3 seconds? Is that possible to have negative time? Yeah, it is. Negative time just means 0.3 of a second before we actually started the stopwatch, right? But that's still, so I think we did, if I snap my fingers, and now, well, I snap my fingers, I don't know, negative 10 seconds was when I snap my fingers. Now it's maybe negative 15 seconds, right? It just means that long before now, right? Make sense? I think that's just so cool that there actually is a reason for this answer. That you can interpret it as meaning something significant. Okay? What else we got here? Anything else? Okay, there's one more kinematics equation I'm just gonna give you. And I don't know if we'll have time to use this or not, but see if you can tell me something unique about this one. I'm gonna write it in purple, because it's a little bit different. So this one is v squared equals v naught squared plus 2a times delta d. A little different than the book, right? And I always use this one even a little differently than this. I prefer to write it as v squared minus v naught squared equals 2a delta d. What do you notice about that equation that's different from all the other ones? Something really special about that one. There's no time. Yeah, that one's independent of time. So sometimes that's a really handy one to have. Because what if, I mean, that pops up sometimes. So let's just take an example. What if we know that, okay, let's say we take the last example, and I want to know how fast the bullet is going when it hits the ground. Okay, so is that it? No. That's it, right there, right? What if I wanted to know how fast it was going when it hit the ground? Okay, I could solve it this way, couldn't I? By finding the time, and then I'd have to go back and maybe use another equation, wouldn't I? Right, if I knew what the time was, couldn't I go back and use the velocity equation? Everybody agree? I could use the equation v equals v naught plus at. I know the initial velocity is positive 1,000. I know the acceleration. I could take that time and plug it in and find the velocity, couldn't I? That's a lot of work though, right? Couldn't I instead, if I just want to know how fast it's going, couldn't I bypass all that and just say, if I know that the initial position wasn't it 300? The final position is 0, and the initial velocity was 1,000. And the acceleration is, let's make things a little bit easier. Should we just say it's 10? Make things a little simpler. Is roughly equal to 10 meters per second squared. What is v final? Yep. Oh, negative 10. Yep, you're right. I gotta rewrite that anyway. That was so messy. So A is roughly equal to negative 10. Now we can use our new equation, right? We don't have any time there, but we can say v squared minus v naught squared equals 2a delta v times displacement. Now what's my displacement in this case? I'm starting at 300 and ending at 0. Isn't displacement always final value minus initial value? So what's that going to be? 0 minus 300.
Negative.
Makes sense, doesn't it? If it starts here and goes down 300, the displacement is down 300 meters, so negative. Okay, we know acceleration. We know initial velocity. So if I just add initial velocity to this side, velocity squared, I get v squared equals v naught squared plus 2a delta d. It's all stuff I know and can plug in, right? So we get 1,000 squared, just leave the units off, plus 2 times negative 10 times negative 300, right? Make sense? Okay, and all that's equal to v squared. So what's v going to be? What's v going to be then? How do I undo a square, in other words? Square rooted. Yeah, so v is just gonna be the square root of all that stuff. 1,000 squared, what's that gonna be? Minus 20 times negative 300, so 6,000, is that 6,000 plus 6,000? Okay, if I put that in my calculator, what do I get? Let's see, I gotta get out of here, don't I? So main, quit. I go square root, 1,000 squared plus 6,000. And I get an answer of about 1,003, let's just say. What if I took it to 3? So about 1,003 meters per second. Does that make sense? It kind of does, doesn't it? If you think about it. Think about the path of that bullet. It's going to leave at 1,000. How fast do you suppose it's going to be when it comes right back by the rifle? Negative 1,000. Yeah, how about that? We'll talk about why that's the case a little later. The trajectory is completely symmetrical. So it goes by with a velocity of negative 1,000. And by the way, this is not a velocity, this is a speed. These are speeds. That's the other thing you got to take into account here. They're not velocities. They're just speeds. So the speed of, we have to interpret what the sign is going to be based on the problem. Okay. So the speed is going to be 1,000 going down, and then it's going to travel that last 300 meters pretty quickly, isn't it? Because it's going so fast. So it's going to accelerate a little bit, but not very much. Just going to add roughly an extra 3 meters per second of speed, right? So that's a pretty handy one to have, but you do have to keep in mind, this is the big thing here, is that whereas these are all vectors, these are not. Whoops, hang on. These are not, all right? That make sense? Okay. All righty. Oh.